Hi, I'm Rob Anthony, and as Dr. Cruz said, the title of my talk is Assembly and Testing of LISA Neutron Detectors. Obviously, LISA stands for Large Area Multi-Institutional Scintillator Array. And I'll go over in a second why they came up with such an awkward acronym. Basically, we and 9 other institutions were selected to build 16 neutron detectors each for use at Michigan State University's National Superconducting Cyclotron Laboratory. The first thing you might be asking is, what types of nuclei will we study with these detectors? Earlier this fine morning, we saw Stephen's talk where he talked about selenium-71, and in the nuclear landscape that's over here, it's proton-rich, so it gives off gamma rays when it decays. And this is an area that we fondly like to refer to as the Wild West. I have a little animation there. The type of nuclei we'll be studying are actually the complete opposite. They're on the other side of the landscape. They're neutron-rich. And so one type of neutron to study is called neon-28. It's over here. And this is the area Dr. K and I like to call, and we coined this ourselves, the exotic East. And of course I have a little image of that. So we were actually just up at Michigan State helping out with an experiment the other day. And they were actually studying neon-28, and here's how you get it. First you start off with calcium-48, smash it into a primary beryllium target, and then you're going to get 32 magnesium and a bunch of alpha particles. Use aluminum to filter out the alpha particles, you're just left with the magnesium. Smash into another beryllium target, and you get neon-28 and some neutrons, which we're hoping to detect with our detectors and hopefully determine the energy and position of these neutrons coming off from here. And here's a quick schematic of the NSCL facility. Over here is where the particles, the calcium-48 is generated. It's accelerated by not one, but 2 cyclotrons, which you're not allowed to get near, especially if you have a pacemaker. This area here is where the first collision starts. It's filtered out here. And then the second collision with the beryllium target occurs here before it hits MONA, which is the existing array. Now with LISA, you'll now have twice the power, and you'll be able to look at even more exotic particles and get even better results. And of course, they went with a weird acronym so they could have Mona Lisa be the name of your arrays. And you've all seen Mona Lisa, so I'll just put a quick picture up there. So how do the detector bars work? Well, the detector bar is made of plastic, which has lots of hydrogen atoms in it, which is essentially protons. And the incoming neutron displaces one of the protons, and basically you have a moving charge coming through this scintillator material. And when a charge is moving through it, it emits a photon. So the more energy that the neutron has, the larger amount of photons you generate, so the stronger the signal. So that's how you can tell how much energy the neutron is carrying with it. You can also determine how the neutron, where it struck the bar, the exact position. And I've created a short animation to show how this works. What you're going to see is a neutron come in and strike the bar. It's going to be converted into a photon, which will be cast through the lines. Then you'll see an electric pulse travel through to this device called a time-to-amplitude converter, which basically takes the difference in arrival times of the 2 signals, and based on how large the magnitude of the difference in arrival time, it'll create a voltage pulse. And that'll be sent to Mr. Computer here, which crunches the numbers and puts out a pretty graph. So without further ado. And then we start counting on our time-amplitude converter times. And then you get a voltage out based on the difference in arrival times, and then you can know your position. Cool. So this summer, we assembled these detectors, and the majority of the construction is actually assembling these PMT bases, which consists of about 6 parts. There's a magnetic shield around the whole thing to kind of keep magnetic field lines from equipment in the lab from interacting with it. There's a photomultiplier tube, which of course takes your scintillated signal and amplifies it and converts it to an electric signal. There's a PMT socket, that's kind of where all the electronics are. A tube, which just, yeah, it's just what it sounds like. It just kind of holds the whole thing together. A voltage divider, which helps to set up the different potentials in the PMT to make sure that you have a cascading effect as the photons travel through it. And then a base where we hook up all of our electronics equipment to power the PMT and to get data from it. There's a picture of me soldering some stuff, and Alex there is applying the PMT to the tube using some optical grease, and have a bracketing assembly. So lots of soldering, lots of gluing, lots of fun. We also fabricated nanosecond delay boxes, and these are really fancy. Basically, if you watch my animation, you saw that it took some time for the pulse to travel through the wire. Well, we're going to delay the signal. We're not using any fancy logic or computer chips. We're just using lots of cable. So if you want a 100 nanosecond delay, you use so many meters of cable. If you want a 20 nanosecond delay, you use 1/5 amount of cable. So it's just all wrapped up in there. This is basically just a box that we got that you can put a VCR or anything in. I used a drill press to drill out all the holes and put in the female LEMO connectors in there. And then all the wire was soldered on the back with many more hours of soldering. And this will be used up in Michigan State for the LISA array. Once we got the detectors all assembled, we had to test them. And the first thing that's crucial is that you don't have any light leaks, because your signals are scintillated light, photons. And if you have ambient light coming in, well, that's not any good. So what we did is we powered up each PMP to 1500 volts under ambient light. And what we were looking for was to see if this baseline up here would fall below ground, which would mean that our PMT is essentially being bombarded with photons that aren't related to scintillations. So if that happened, regrettably, we would turn off the lights and we'd start shining a flashlight all around the thing. And it'd be pretty obvious when you found a leak, because the baseline would just crash on you. And it'd be like, well, there it is, and you put a little more silicon on it and pretty much seal up the light. The second test was gain matching the tubes. So each of these photomultiplier tubes have a different gain associated with them from the factory, and it's up to an order of 10 magnitude. And what we did is we used a muon peak. Now muons are a fundamental particle that's constantly being bombarded with, and they're in cosmic rays, and they're depositing energy in our detector bars. So we used a medium gain tube to get kind of a baseline place where this peak should be. And then we saved that, and then for each subsequent PMT, we tried to adjust the voltage that we drove the PMT with to get the peaks to line up, so that all of our PMTs were having the same gain. And here's a chart showing, this is what the manufacturer gives you as anode sensitivity in amperes per lumen, and that over there is the gain that we ended up using to drive our PMTs. And you can see it's pretty linear. Third test was to see what the light attenuation was of the detector bars. And what we did is we used a cobalt-60 gamma ray source, and we started at one end of the bar and moved it towards the other end. So it's getting further and further away from a PMT. And what should happen is as the gamma ray source goes further away from the PMT, the scintillations are going to be attenuated within the bar. So you'll see this peak right here start to move to the left as you move the source further and further away from the PMT. And here's a chart showing the exponential decay in signal intensity as you move away from the PMT. And this is what we expect from multiple physics laws. One final test is we determined, we did a position spectra, kind of like in that animation I showed you. But here we just used the muons again. So the muons would be hitting randomly anywhere on the bar. There's an equal probability that they hit on this side of the bar, on that side of the bar, in the middle. So you expect to see just like a flat peak because, it's equal probability of hitting somewhere. And that's pretty much what we see there, is for the left to the right side of the bar with an equal amount of muon striking. So that was the final test, and we got all the bars packed up, and they're headed up to Michigan State here in the next year to be used with the larger array. And here's a picture of us with the existing array. There's Mona in the background in the vault. And right now they're currently running an experiment to test neon 28, as I said earlier, in this vault. And no one's allowed in there. It's 4-foot thick doors to keep you out. And yeah, thank you very much. Thank you, Ohio State University, Michigan State, and of course National Science Foundation for feeding.
many hours of soldering are involved in this?
Probably like 50 or 60. Well, there's also some extracurricular soldering in the car too.
So do the police detectors work in a similar fashion as the motor detector does?
Oh yeah, they're identical.
Yeah, that's okay.
How do you control for to make sure all the wires are exactly the same length and the thing's designed to give you a slower signal
In the
in the detector? The delay box.
oh, how do we make sure all the wires are the same length? Meters thick. Basically, we determined that there's a delay of 5 nanoseconds per meter of cable, and then you just measure it. And then to make sure I got the correct delays, I use what's called a pocket pulsar to send a pulse through there, and I use an O-scope and I measure the delay of the reflection coming back from the wire. Does that answer your question?
Yeah.
Just a little more detail about that. So Alex actually measured tested that that standard about 5 nanoseconds per meter right here at Ohio Wesleyan. We didn't have quite as fancy of a setup, but pretty close to the same thing. So we could actually test that by looking at pulses that travel down the wire and then reflected back because of a what's called an impedance mismatch. It's kind of like shaking a wire, and when you shake it, it's attached to a wall on the other end. You'll see a wave pulse reflect back. So, and then between Alex and Rob, they both work together to cut the wire. They're not all the same length. They're different lengths depending on how much delay you need. And they carefully measured that and soldered it into the box, and lo and behold, we get 2 of these boxes. And then just a quick note about Becca's question. They're not identical. In fact, but they're very similar. The photomultiplier tubes for the Lisa detectors actually have a higher intrinsic gain than those from Mona. They're made by different manufacturers.
Somebody else has a question. Yeah.
So the wire boxes.
Huh?
Boxes that have wires in them? I'm sorry, I don't know anything about this, but is that really, like, is there another way to do that?
I'm sure you could probably use some sort of digital logic to do the delay.
For about $1,000, you can buy a gate and delay generator from Ortec, but for significantly less, you can buy a digital wire.
$19 you can make it.
Perfect physicist solution. I mean, that's. I like it.
Sure.
I can see it.
But very time.
Yes, not cheap on time, but
Cheap
you didn't mind.
I didn't.
Any other questions? Okay. Well, thank you.